So next up, we have our last technical talk of the day, Sarah Osborn, who's going to talk about some of the work she does at the lab. Sarah works in the mathematical algorithms and computing group in me, and has been working at the lab since 2015. She has a PhD from Texas Tech, and her research interests are in uncertainty quantification, parallel computing, iterative methods, amongst others. Primarily, she works in a cyber and infrastructure resilience program. And today, she's going to talk about a couple different things related to her research. She'll start with work she does in large-scale problems, move on to work she does as part of the Exascale Computing Project, and end with the Squirrel framework. I love this name. I loved it for years, to increase resilience against cyber attacks. So let's welcome Sarah.
Right. Let's get into the word. Let's do it. And let's just oh, they were. Jim. Story. Hans again.
Okay, great. Thanks for that introduction, and thanks committee for organizing this great event and then inviting me to speak today. And thanks everyone for attending and bearing it out for the last talk of the day. So without further ado, I'll go ahead and get started. So as Isha mentioned, it's true confession time. I am not a data scientist. As you can see, I'm a computational mathematician by training. So really what I want to talk about here is more coming from a perspective of mathematical modeling and simulation, also with some tie-ins to high-performance computing and software ecosystems. So I'll actually just be talking about two projects today, but I will end on a brief word about Squirrels. So first up is some work that I performed during my postdoc here at the lab on a big topic in uncertainty quantification. So the idea here is in traditional modeling frameworks, we often assume that we can really completely characterize our input. Then we're able to find our numerical solution, U, which is based on our input, Y. However, there is inherent uncertainty in our inputs, especially when we're thinking about modeling real-world phenomena. So this may be something that is, your physical process properties of your materials is affected by some sort of uncertainty, or it could just be due to a lack of data that we can't accurately characterize those inputs. So we want to be able to tackle this problem of this forward propagation of uncertainties. So we're first going to model our input uncertainty using a random field. Then we want to understand how that uncertainty is going to propagate through our numerical solution, leading to uncertainty in our output. And really that's what we're interested in, is quantifying this impact of this uncertainty on our model outputs. So we're going to particularly use a field of sampling methods, namely these Monte Carlo methods, for this problem. So here we take realizations of our input random fields, then generate solution samples based on our numerical solution, kind of represented as the model in the slide, to be able to then construct these sample statistics of our counting instead about. So for my actual problem of interest, we were really interested in understanding uncertainty within subsurface flows. So the idea here is that we do have this uncertainty in our permeability field, K, and this is often due because we can only measure at a few locations in our domain. So to overcome this lack of information, it's a pretty common practice to assume that our K, this permeability coefficient, is a spatially correlated log normal random. And so now, once we insert this uncertain random field k into our Darcy's law equations, now this becomes a stochastic equation. And now these pressure P and our Darcy flux are now also random fields. So now we really need to understand how we can come up with a solution, in particular, this expected value of a particular quantity of interest that we care about. And this model problem comes up in a lot of petroleum engineering applications, which is something that why we were interested in this particular model. All right, so kind of Monte Carlo method via pictures. So the idea is here that we generate many realizations of our input coefficient, then use our numerical solver to find many different samples of our solution. And then here we can compute the sample average to approximate this expectation of our quantity of interest. And what's really nice about using a Monte Carlo method like this is we do not have to change anything about our underlying numerical solver. So this is called a non-intrusive method. So we're able to do this uncertainty quantification without having to change our kind of non-intrusive. We don't need to change anything in our problem formulation. However, we do just need to run our simulator, which already used HPC resources. So now we just need to do it many times. So to see now kind of that method now via equation, this is our single level Monte Carlo estimator for our expected value of our quantity of interest. If we take a look at the mean square error, we see that it breaks into two pieces. So if we want a high accuracy of our quantity of interest, we first need to make this quantity smaller. This is basically our estimator variance, so the sampling error. So basically we need to make many samples. That can be expensive. Also, to tackle this piece of the error, this is our bias, which in our case is our discretization error. So again, to get those highly accurate solutions, we need to use a fine spatial resolution to make this discretization error smaller. Again, this leads to more expensive computations. So overall, this can really get prohibitively expensive. So that is why we switched to using this widely used multi-level Monte Carlo method. And the idea here is this is a variance reduction technique. So here we are able to translate that single level Monte Carlo estimator that we saw in the previous slide using this telescoping sum formula. Then if we look at the mean square error of this multi-level Monte Carlo estimator, we see it breaks into three pieces. The first piece is a fixed cost, but now it is independent of H, which is our spatial discretization parameter. So now we don't necessarily have to worry about it for this piece of our error. Our middle piece here still involves the variance. However, now that we're taking the variance in this correction term, that's going to be significantly smaller than if we were just looking at the variance of our quantity of interest estimated on a single level. We also still have this discretization error piece, but essentially we can kind of handle that. So now with using the multi-level Monte Carlo applied to our particular problem of interest. So this is an example of using it for a three-level, multi-level Monte Carlo estimator. So we have our fine resolution, so still using that more expensive spatial discretization, but the trade-off is we only have to compute a few samples here. Then we can spend the majority of our time computing samples on our coarse resolution, which is less expensive. And there are heuristics for how to calculate the number of samples and the number of levels you should take. All right, so now for really what the research question here is now, how do we actually generate those realizations of that input random field? And in particular, how do we do this on a hierarchy of spatial discretizations? So typical methods involve a dense eigenvalue computation, which this can really be a bottleneck, especially when we're thinking about when we have regimes where we have a lot of stochastic degrees of freedom. So what our method does is we formulate generating these input realizations by solving a stochastic PDE. Again, without going into too many details, we have this PDE listed below, and if we are able to solve that for theta, that is going to give us a single realization of our Gaussian field, which is what we need for input into our multi-level Monte Carlo estimator. All right, so we're going to use a finite element method. We get a saddle point linear system. Again, the main thing with this method is we can leverage existing expertise in scalable solvers and preconditioners, and then their software implementations to solve this problem. So we're able to do this in a hierarchical manner because we need to be able to find these samples on those different levels in our multi-level hierarchy. So we can then perform this in a scalable way without essentially having to reinvent the wheel too much, because we are able to use this kind of existing expertise to solve this problem. So there is a wrinkle in this methodology. If you can see here on the left, we have this red on the boundary here, and basically that is representing this artificially inflated variance for our sampled realizations using our methodology. We don't want this. So we worked with a really great summer student who helped us come up with a methodology where we could embed our original domain into a larger domain, solve our PDE there, map it back to our original domain. So now we see that we don't have this artificially inflated variance on the right once we do this procedure. So now to see this in action, this is a weak scaling study. So basically here, what we are doing is we are fixing the number of degrees of freedom for each process, and then we are scaling it up, increasing the number of processes. And so to interpret this, basically we want as flat of lines as possible. So we see kind of the hash line here is our kind of optimal scaling. We see that on our fine level, we're close to optimal. We're about 74% parallel efficiency for our fine level. So we were pretty pleased with this result. And more so, this is just kind of a demonstration that we really can run this at scale, be able to handle these applications where we do have a large number of degrees of freedom. All right, so now to bring it back to our full multi-level Monte Carlo simulation workflow, basically there's two main pieces. So we first need to solve this stochastic PDE to find that input realization. Then we need to plug that in to our solver for our Darcy's flow. And then finally, we do this over a loop, basically generate many samples on many different levels. And then finally, kind of at the end of the simulation run, we perform this post-processing step to compute our expectation of our quantity of interest.